Hi everyone. Welcome to the USACO February workshop. In this session, we'll be going over the gold problems from the USACO February contest. This workshop is co-hosted with our sponsor, XCamp. XCamp is a Silicon Valley-based institute that offers coding classes for middle and high school students so that they can achieve success at contests like USACO and beyond. And XCamp has also provided us with the discount code CPI 100. So if you're signing up for XCamp classes, you can use this discount code. For the schedule of our workshop, we will be going through the 3 problems from the USACO Gold Contest, and we'll have Evan from CPI be teaching 2 of them, and Yizhong from XCamp teaching the second problem. So let's get started.
All right, thank you, Maggie. So let me share my screen if I can figure that out. Okay, so yeah, hopefully you guys can see my screen now. Let me open chat. And well, first of all, I would like to say that I'm very excited to be here, and I'm honored to be one of the presenters for this workshop. Whoops. So yeah, let's just get started. So like Maggie said, I'm going to be explaining the first and last problem for the previous USACO contest, gold contest. And yeah, let me just quickly show you the first problem of the contest. I'm going to quickly summarize the problem just so that we're on the same page. So this problem, we are given, there are n cows. So in this case, 4, and each cow has a list of numbers. So these numbers mean that, for example, cow 1 prefers gift 1 over gift 2. Cow 1 prefers gift 2 over gift 3. Cow 1 prefers gift 3 over gift 4. And yeah, and initially, cow I is given gift I for all I. And you know, there is a list of favorite to least favorite gifts for each of the cows. It's given in input. After that, the problem gives you an integer q that is the number of queries for the problem. Each query, there is a string of length n, which in this case is 4. It tells you the type of each cow. So for example, in this query, each cow is the type of each cow is H or Holstein, I think. I'm not sure how to pronounce it properly. In this case, first 2 cows are H's, Holsteins, and these 2 are Guernseys. For each query, you want to calculate how many valid reassignments there are. A reassignment is basically each cow, the cows in each for each type, either G or H, you reassign the gifts among themselves. For example, here, the 4 cows can reassign the gifts among themselves. So instead of cow 1 having gift 1, cow 2 having gift 2, gift 3, and gift 4, we can have, for example, 4, 3, 2, 1. However, only the only the reassignments that are valid are counted towards the answer for the query. So again, the problem statement says that basically, if every cow, after the reassignment, receives a gift that he or she likes more, or if the cow doesn't receive a new gift at all for each of the cows, then the reassignment is called valid. For example, we can swap the gifts between cows 2 and 3, and cow 2 will be happy because, well, the cow will receive gift 3 instead of gift 2. Cow 3 will receive gift 2 instead of 3. So yeah, that's the problem statement. Now let's jump straight to the solution because we don't have that much time. Whoops. So let me just talk about the solution now. My solution does assume that you guys have some background knowledge on dynamic programming and a bit of graph theory. So if you don't know, then it's going to be hard to comprehend for you. First of all, let's simplify the problem by pretending every cow's type is Holstein from now on. This will make it easier. It doesn't matter if you pretend every cow's type is Guernsey. As long as every cow's type is the same, it will be simplified. Okay, we'll take the types into account by solving for Holsteins and Guernseys independently later on. Okay. Well, now notice that for almost every gold and platinum contest, there's a dynamic programming problem. And here, dynamic programming, it's linked to a, let me paste that into the chat. It's linked to a USACO.guide section. It's a gold topic. And actually, this is exactly a dynamic programming problem. Now, seeing that n is smaller than, not, or equal to 18, not equal to, we know that the intended solution's time complexity might involve a 2 to the power of n term. Okay, and what does 2 to the power of n remind us? It reminds us of subsets. And also, it reminds us of bit mask dynamic programming. It is also another section in the USACO.guide website. All right, so now let's let DP bit mask be the answer. Whoops, ignore that. Be the answer for the subset of cows represented by bit mask. As a refresher, if cow I is encoded in bit mask, then the ith bit in bit mask will be 1 in its binary representation. Here we then will logically, we will ask, how do we do DP transitions? That's very important. We don't know that yet. Let's continue. So part 2 of the solution. Pretend bit mask represents the subset of the cows 1, 3, 4, and 8. Okay, it's just an example. It's just a random subset of the cows. Use a vertex to represent each cow. So now we're using a graph to represent this. Then draw an edge x to y. It's a directed edge if cow y prefers cow x's gift over gift y. The result could be this. I just made up this example. It could be something else. As you can see, cow 4, there's an edge between cow 4 to cow 3, and well, you know how it goes. Then we want to choose a subset of edges to keep. So I chose a random subset of edges from this graph, and this is the result. Let me move this right here. Okay, now, next step, for each edge x to y, cow x will give her gift to cow y. Okay, and notice that the result will be a reassignment. Okay, let me. So that's why we are doing directed edges in this graph. It's intuitive because, for example, cow 4 can give a gift to cow 3. Cow 3 can give a gift to cow 8. Cow 8 can give a gift to cow 3, and so on. Okay, the result after each cow gives her gift through the directed edges, following the directed edges, will be a reassignment. Okay, just like what the problem statement says. However, notice that, well, not all subsets of edges are valid, actually. So here, this example is valid because cow 8 will give gift to cow 3, cow 3 will give a gift to cow 8. Each cow in the end will have 1 gift. And yeah, this is an invalid example. So why is it invalid? Because, well, first of all, cow 4 gives a gift to cow 8, cow 8 gives a gift to cow 3, cow 3 gives a gift to cow 1, and cow 1 gives a gift to cow 3. It's invalid because cow 3 is given both gifts 1 and 8. Okay, 8 gives a gift to cow 3, and there's a directed edge between 1 and 3. Okay, so cow 3 is given 2 gifts, but it only gives away 1 gift. In the end, it has 2 gifts, but a cow cannot have more than 1 gift. Okay, so that's why it's invalid. Now, using this graph representation, we can define DP bit mask in another way. We can define DP bit mask to be the number of valid subset of edges. Okay. To define what a valid subset of edges is more rigorously, read this. A subset of edges is valid if and only if every vertex has exactly 0 incoming and 0 outgoing edges, or has exactly 1 incoming and 1 outgoing edge. This makes sense because, well, a cow can't, if it receives a gift, it needs to give away 1 gift in order to have 1 gift in the end. Okay. Now you might ask, actually, why can't we have for example, a cow having exactly 2 incoming and exactly 2 outgoing edge? Well, you could, but if we do, we can always represent it with like exactly 1 incoming, 1 outgoing edge in the end. So I drew something here in the whiteboard that will help you visualize this. For example, like what I just said, what if cow X has 2 incoming and 2 outgoing edges? In the end, cow X will have exactly 1 gift, right? Oh, and by the way, there are other vertices and edges that I didn't draw in this graph. Pretend every cow in the end will have 1 gift. The question is, can we have this? I mean, this is a valid subset of edges, right? Well, it is, but notice that, for example, if cow A gives her gift to cow X and cow X give cow A's gift to cow C, that's just like, that's the same as cow A giving a gift to cow C directly. There's no need to pass along a gift through several cows, just give the gift directly. So that's why we can have this definition, exactly 1 incoming or exactly 0 incoming and outgoing edges. It is loading. Okay. Now, furthermore, if a vertex satisfies condition 1, which is 0 incoming and outgoing edges, add a self loop to itself so it satisfies condition 2. Okay, that makes things convenient on the next slide. So let me tell you why. It makes things convenient because of the definition of circle subgraphs. So I just made up the term circle subgraphs. It is, well, a circle subgraph is basically like, well, first of all, a circle graph is a graph with n vertices, n edges, and each vertex has exactly 1 incoming and 1 outgoing edge, and the resulting circle graph will have exactly 1 cycle. It's different from a cycle because cycles can share vertices, okay? But a circle graph cannot. Here's a circle graph. It's intuitive. The name is intuitive because it kind of forms a circle. It's more like a regular 10-sided polygon, but it's somewhat of a circle. Here is a circle graph. Okay. Notice that it satisfies all of the conditions, all of the properties of a circle graph. It kind of looks like a circle if you draw the edges like curved instead of straight. And here's another circle graph. Okay, that's if we don't have that self edge for lonely vertices, then it won't be a circle graph. That's why we added for each vertex that satisfies condition 1, we add a self loop to itself. Okay, so all right. If you guys have any questions, by the way, you can put them in the chat. I'll be happy to answer them. This might get confusing at times. Then we can represent dp bit mask in another way. So dp bit mask then becomes the number of subset edges such that the resulting graph consists of just circle subgraphs. Okay. Yeah, but I haven't proved why the resulting graph will consist of just circle subgraphs. I feel like it's easy to prove it. If you don't know why, you can ask me. I'll quickly prove it to you if you want to. Okay, now, for all circle subgraphs consisting of nodes v1, v2, v3, all the way up to vk, we want to add this value to dp bit mask. What do I mean by that? Okay, so first of all, what does this expression mean? Bit mask backslash curly braces v1 and v2 all the way up to vk. What does that mean? Well, basically it means remove the vertices v1 and v2 all the way up to vk from bit mask. Okay, so that's what it means. So basically this just means that for all circle subgraphs in bit mask, remove the subgraph and add the resulting answers. Well, basically add this into dp bit mask. It's intuitive, especially if you know dynamic programming. If you struggle with understanding this, then you might not be too familiar enough with dynamic programming. It's fine though. You can still ask me any question that you have, and I will answer it for you if you don't understand. However, there is something crucial I would need to notice that about this. We might overcount if we just add bitmask backslash v1, v2 all the way up to vk into dp bitmask. Because, well, for example, if this is the graph, these are the vertices that bitmask encodes, then we might first take out this circle subgraph and then add the answer for the resulting vertices, or we might take out this vertex first and then add the resulting answer. Both of those will count this subset of edges as in its answer, so we will overcount. Okay. Again, if you have any questions, you can ask me. So to account for overcounting, we can make sure that v1 is the vertex with the smallest ID in bitmask to not overcount. Okay. Again, not going to prove it here. Feel like it's intuitive enough, and we have limited time. So yeah, if you don't know, ask me in the chat. All right. So one last slide before we look at the solution. Okay. So let's add one more dimension to this DP array. Instead of DP bitmask, we will add another dimension. We'll call this current node or I. And for bitmask, we'll just use B. What this means is that, well, remember we're trying to find how many subset of edges results in just circle subgraphs. Well, we will construct a circle subgraph. So we're currently constructing a circle subgraph. Okay, the current node I is the current ending node of the incomplete circle subgraph. So if you look here, we're trying to construct a circle subgraph. So we have the edges from here to here, here to here, and then here to here. We have ended at this node currently, and this is node I. Okay, and any green node J is a node such that we can have an edge I to J, unless if J prefers her own gift over gift I. So for example, the current node can have an edge to 2 or to 6 or to 13, unless of course if any of those vertices, any of those counts, if for example count 13 prefers gift 13 over gift 8, then we cannot have an edge from 8 to 13. Okay, and notice here that the green node with the, oh yeah, by the way, bitmask B encodes all green nodes. Then notice that the green node with the smallest ID is the starting node of the incomplete cycle. So the cycle, sorry, I don't mean the cycle, I mean a circle subgraph. So this circle subgraph that we're currently trying to construct, it started at this node, and this node is the vertex with it's the green node with the smallest ID. Why? Well, because we made V1 in our circle subgraph the vertex with the smallest ID in bitmask. So that's why the green node with the smallest ID is the starting node, the incomplete cycle. That makes things inconvenient because we don't have to add another dimension into our DP table. Okay. All right. And also just note that only the subset of edges that we keep are shown on the right. So there might be other edges that are other direction edges that I don't show. But the edges that we currently keep in our circle subgraph are definitely shown. Okay, so now that we went over the solution, I hopefully I didn't go over time. Let's look at the code in C++. Hopefully, this will clear up some of the details that I didn't explain in the slides. So I will paste you the link in the chat so that you can view this. So here's the code. It's in C++. I don't have a Java nor a Python solution. There is a Java solution in the official editorial, so you can view that if you want to. Python, I'm not sure whether you can pass in Python. So anyways, we declare some variables, constant variables, n is the maximum number of n. Well, I added 2 because I wanted to. MM is basically the maximum the maximum value of the bit mask in DP, okay, is 2 to the power of 18 plus 5. And we declare other variables here. So N, Q, you know what those are. W. So Wij means which position in Chow I's list of favorite numbers is integer j. Okay. Basically, W1, 2 will be W2, 3 will be 2 because in Chow 2's list of favorite to least favorite numbers or gifts, number 3 is at position 2. Okay, so that's what the array W means. Okay, then we have a function bool that basically means that basically returns, can Chow I give a gift to Chow J? In other words, does Chow J prefer gift I as much or more than gift J? Okay, and we use our table W to help us with that. L bit basically returns the index starting from 0 of the lowest bit in the binary representation of X. Okay. Oh, by the way, all cows and indices are 0 index because we're using bitmask dynamic programming, and bitmasks, it starts with 0, the index. So yeah. Anyways, here we will default to 0 if X is 0, right? We will never return anything if X equals 0. So we'll just default to 0. You'll see why that's convenient later on. Here in our main function, we take in the input and we initialize the array W. Okay, and here is the loop that's interesting. So this is the loop that calculates the table DP. So for each of the bit mask B, first of all, we can calculate S directly because, well, like I said in the slides, it's the lowest green node in bit mask. Okay. And then we will iterate through all of the current nodes of this bit mask. So I going from n minus 1 all the way up to 0. We're looping backwards because we need to calculate, for example, DPI 6 before DPI 5. Okay, we could use recursion instead of doing this nested for loop, but nested for loops are faster. Here, first of all, we check whether b equals 0, whether there are no cows encoded in bitmask, or whether there are no vertices encoded in bitmask. If so, then there are no more circle subgraphs to construct. So we set bi to be 1. There's only one way to construct circle subgraphs, and that is to not construct any. And then we continue. And then we check is whether I is not in the starting node, first of all, whether I is not the starting node, and if I is green. So if I is not the starting node and I is in bitmask, we continue because that's impossible. For example, here, our current, where's my mouse? All right, so here, our current node can't be green because it cannot have an edge directed towards itself. That would not make a circle subgraph. So that's why we continue. And then we check, can Chow I give a gift to the starting node S? We check that by seeing whether, well, first of all, I can give a gift to S. Okay. Then, well, we don't check whether S is green because, well, S is already green. Like I said in the slides here, it will always be green. And then we create a temporary variable B2 is equal to B, the bit mask. We remove S, the starting node, from B2, and we add DP BI. We add this value into our into here. This basically means, so after removing the starting node from the bit mask, we want to start our cycle, and the start of our cycle is the L bit, lowest bit in B2. Okay, so when we have reached here, we have finished one circle subgraph. Now let's try something. Let's try to let I give a gift to another cow instead, J. That is not the starting node. So for all J, if J is green, and you can have an edge between I and j. We will create a temporary variable like we did here, remove cal j from our bit mask, and add dp b2j into our answer dp bi. So yeah, we basically continue our circle subgraph in our loop here. We finish it here. So that's why we don't delete or remove the starting node from right here. Okay, let me go a little bit quicker because we are running out of time. So here's where we really answer the queries. So for each of the queries, we take in a string s. Okay, everything is 0 next again. We have a bit mask h, host signs, and a bit mask g, the currencies, and for each of the characters in s, if the ith character is h, then we put count I into the bit mask h, otherwise we put the count I into bit mask g. Okay, so these two bit masks in the end will encode the cows, the host signs and the currencies, and we just solve them independently. So first of all, we find, we multiply, we'll find dp, we already found it. So we multiply dp h, l bit h. So basically we are, for example, if there are no edges here, and this represents the subset of host signs, then we are starting our circle subgraph at the starting node. Okay, and similarly for currencies, we are doing the same thing. And in the end, we multiply them because yeah, they're independent, and yeah, and that's the entire solution. So yeah, this problem is not easy, nor is it easy to explain. Hopefully I explained it clearly. If you have any questions, again, you can put it in the chat. Otherwise, we can move on to the next instructor. All right, let me stop sharing my screen.
Thank you, Evan. Now I'll have Yizhong present his solution to the second problem. Yizhong, if you're talking, I can't hear you. Can anyone else hear him? Still can't hear you.
Can you hear me now?
Yep, we can hear you now.
Okay. Sorry. Okay, should I share my screen?
Yeah, you can share your screen.
Okay. Okay. No. Okay. So I'm Yizhong, and nice to meet you. Today I'm going to share my solution about the second problem of gold. Okay. So first, let's review the definition of the expected value, which is about this problem. We consider a random variable x with a finite value list. Then we define the expectation of x as x1 p1 plus x2 p2 plus blah blah plus xk pk. That is the expectation of x. So in this problem, we have the binomial distribution. That is, there are n independent experiments. Okay, in this problem, that is, we have t test cases, right? So for each test case, the successful rate is p. In this problem, p is 0.5%, right? So the successful rate for each is 0.5, and also 0.5 to fail. Then we suppose for one submission, we suppose x is the number of successes, which means the score we get, okay? Then we have px equal to I is c. You know, c is the combination. C and I divided by the nth power of 2. Okay, do you know c? Okay, c is c and I equals to that's c and I. Okay. So then we turn to the problem. We have two test cases, each worth 1 point. Okay. To answer. The answer of each one is either yes or no. But you don't know how to answer these test cases. So your policy is you print the right answer for the sample test case and the random answer for the other test cases. Since you print the random answer, so the success the successful rate for each test case is 5%, 50%, right? After a submission, then you can see the points you get. And after you see your score, you can decide whether you submit the code. But there is a limit that you can submit at most K times. The score you got, the score you get depends on the last submission. Okay. So because your program output the random results, so the only decision you need to do is decide whether you resubmit the code. First, we can analyze this problem. We can know that because you can always pass the sample, right? So you just only focus on the other test cases. If you feel difficult to solve this kind of problems, I think this problem is a little bit difficult. If you feel difficult to solve it, you should always start with the simple cases. What is simple case? First, K equal to 1 is simple, right? You can only submit once. So the expected value is T times 0.5. So it's simple, right? You just ignore the sample case. The sample case you can plus 1 after the final solution. Okay, so if K equals to 1, it's simple. Then we go to 2. K equals to 2. So if K equals to 2, first we need to submit once, right? And after the first submission, we need to decide, should I resubmit after the first submission? It depends on how much score we get in the first submission, right? If we get a really high score, like if T equals 10, if we get 10 or 9, something like that, we say, oh, it's enough. Okay, we just get 10 or 9. It's a high score. Because if we do the submission, then we will find that the score in the first submission it's gone, right? We cannot use the score in the first submission if we do the second submission. So if we get a really high score, then we do not do the submission. But if we get a very low score, like 1, 2, 3, or something like that, sometimes okay, I resubmit, and maybe I can get a higher score. So what is this line? Then we can analyze if we resubmit, we have only one chance because K equals to 2. That means we can only submit at most twice. So if we resubmit, then we only have one chance. So the expected value is T times 0.5, right? This is the conclusion of our previous analysis. So then the line is T times 0.5, because if the first submission gets a score lower than T times 0.5, then we can do a transformation. Then the expected values comes to t times 0.5. This is higher. But if first we get if we get a score higher than t times 0.5 in the first submission, then we should not resubmit, because if we resubmit, then the score decrease to t times 0.5. We don't want it, right? Because it's decreased. So then the policy is very simple. That is, first we do a submission, and if we get a score higher than t times 0.5, then we get the score. We just quit. Okay. If we get a score lower than t times 0.5, then we do a resubmission. So that is the case of k equals to 2. How about k equals to 3? For k equal to 3, equals to 3, that is if first we submit, and if we get a score, we do a resubmission, then you will find that we get a expected value of k equals to 2, right? So the line is the decision line is the decision line depends on the expected value of k equals to 2. If we get a score higher than the line, then we quit. If we get the score below the line, then we resubmit. So then we have the policy. First, we define FTK to be the expected value of t test cases and at most k submissions. When we submit and get the score, the policy is that if score is smaller or equal to FTK, TK minus 1, we resubmit. Or we do not resubmit and take the score. Okay, do that make sense? So then we know the policy, right? This is optimal policy. But once we know the policy, how to calculate FTK? First, because we need to check if score is smaller or bigger than FTK minus 1, right? So first, we need to calculate FTK minus 1. And because first we know FT1, right? So then we can know FT2, FT3, FT4, and FTK. And if we calculate FTK minus 1, then we let L to be floor FTK minus 1. Then we enumerate the score we get in this submission. For the score smaller or equal to L, for this kind of score, we need to do a summation, so we can get a expected value of FTK minus 1. So we add P score times FTK minus 1 to FTK. Remember that Px equals to CTx divided by the t's power of 2. Okay. For score is bigger than L, we need to add P score times score to FTK. Because if score is bigger than L, then we just take the score. So we add the expected value is P score times score. Because we can pre-compute something about P, right? Because P is only depends on T. T is fixed. So to speed up, we can pre-compute prefix sum of P score. We always use the prefix of P score. We pre-compute the prefix sum of P score and then times FTK minus 1. We add this term to FTK. And we always use the suffix of P score times score, right? So we can pre-compute the suffix sum of P score times score. And then the calculation of this part is O1, right? But T is very, very large. It can be a mass power of 10. So the complexity is OT plus K. Because we need to do each K one by one, right? So it's too slow. How to speed up? Let's review the process of the process to calculate FTK. First, we need to calculate FTK minus 1, right? And when we do the when we do pre-computation, then we can define A as the prefix sum of P from 0 to L, and B to the suffix sum of P from L plus 1 to K. Okay, a suffix sum of P I times I, and then we have FTK equals to A times FTK minus 1 plus B. If L remains the same, if it doesn't change, of course it will change, but first we suppose it doesn't change. Then we have FTK equals to A times FTK minus 1 plus B equals to A times FTK minus 2 plus B, then plus B. So the relationship of FTK and FTK minus 1, FTK minus 2 is FTK equals to A squared times FTK minus 2 plus AB plus B. We just do a simple calculation, okay? And then we can know the relationship of FTK between FTK and FTK minus 3, FTK minus 4, something like that. So we have FTK equals to, if L remains the same, then we have FTK equals to the i's power of A times FTK minus I plus I minus 1's power of A times B, blah, blah, and finally we have FTK equals to i's power of A times FTK minus 1 plus 1 minus i's power of A divided by 1 minus A times B. So we have this equation. Do that make sense? Okay, so but if L change, then we cannot use this, because if L changes, A and B will change, right? So this equation will not is not correct if L and A and B change. But we'll find that FTK is increasing with K, because if we have more chance to submit, of course we can get a higher expected value, right? So L is also increasing. If L is increasing, first L is T divided by 2, right? And the upper bound of L is T. So L only varies at most T divided by 2 times, from T divided by 2 to T, right? So we have the final solution. First, we can know that ft1 equals to 2 divided by T, right? T divided by 2. L, and we let L to be the floor of this value. Then we try to find the biggest X that floor ftx equals to L using binary search. That means we find the biggest I to satisfy this equation, because this equation can be calculated in O log and O log K times. Okay, because we only use the power function in this equation, so it's O log T. Oh, sorry, O log K. So we need to find the biggest X that we can use this equation to calculate. And then, so how to find biggest X? It's easy, right? Because if we just do binary search, something like if the result of calculation is bigger than L, then we go to the small part, or we go to the large part. Then we find the biggest X that the floor ftx equals to L. If X bigger or equal to K, then we can find the final answer, because we can use the equation to calculate ftk, right? Else, we do the next step. That is, we set L equals to floor ftx x plus 1, because ftx is the biggest X that floor ftx equals to L. So this one is bigger than L, right? And then we go to B to do the next step. Because L varies at most, L, sorry, not L, L divided by 2. T divided by 2 times, sorry. So the total time complexity is OT log square K. We have 2 log. One log is for the power, and another log is for binary search. Okay. So this is my solution. Can you do it in OT log K? Okay, if you want to do, of course, T log square K can pass all the test cases of this problem. And if you want to do it in OT log K, you can first you come up with this equation, and then you do not use binary search, use a doubling. Because when you use doubling to find the biggest x, you do not use a power. Because I is doubling. First, you get I as 1 and 2 and 4 and 8. So you only need to use square to compute the i's power of a. Because square is 01, right? So then you do not need to do the power function in O log K. Then the total time complexity is T log K. Okay, but OT log square K can also pass this problem. So then I want to share my code of this of OT log square K of this problem. First, this is the main part. We define low and the expectation, which means first we calculate ft1, right? I equals to 1, and low is t divided by 2. Of course, we have a floor function, but in C++, we do not need floor function. Okay, and then expectation is t divided by 2. Then we do a binary search to find the biggest x, and I will show the binary search function after it. And then we find the biggest x. Then we use a function. The function is this equation. This equation is the function, and I will show it later. If I plus next I bigger or equal to k, that means the biggest x is bigger or equal to k. Then we can calculate it by equation 1. Else, we do the next step. Okay. So, what is function? Function is all about the equation 1. A and B is A and B. Okay, and the F is FTK. We define it as F, and in X is I. It's here. Oh, sorry, F is FTK minus I, and X is I. So we need to calculate FTK with this function. Okay, and binary search it's very easy, right? If you know the binary search, then you can write this code. We binary search in 1 to k, and if function ABF made bigger than low, that means it does not satisfy this one because it's bigger than low. So we go to the left part. We let R to be mid, go to the left part, or we go to the right part. Okay. And that's all. Do you have any questions?
Okay, if no one
Okay.
has any questions, then we can move on to the third
Sorry,
problem.
maybe I made a mistake.
Oh,
C and I equals to this one, not n minus I plus 1. Okay. Sorry.
okay. Thank
All right.
you, Yizhong, for your presentation.
Thank you.
And we'll go back to Evan for the third problem.
Okay. So
Okay.
let me share my screen. Okay, so I'm going to be presenting the third problem now. Let me just quickly show you guys the third problem. So basically, we got n cows on a coordinate plane, and each cow, well, there's an edge between every pair of cows. The edge's weight is the distance between two cows squared. Okay, you want to link up, you want to have n-1 edges so that every cow can through some edges reach every other cow, and you want to output the minimum cost. Okay, so that's the summary. Nice and easy to summarize. Let me just zoom in. Okay, so first of all, this problem immediately seems like a minimum spanning tree problem. Let me paste it into the chat because you guys might want to see that. So that's the section on USACO.guide for minimum spanning tree. If you don't know what a minimum spanning tree is, it's going to be a little bit difficult for you to understand this solution, just as a heads up. So if we do use a minimum spanning tree algorithm like Kruskal or Prim's algorithm, it's going to be hard to pass the time limit because there are going to be n squared, theta of n squared edges. Okay. Therefore, we must eliminate unnecessary edges in order to pass. We can still use the minimum spanning MST algorithm, but we need to eliminate unnecessary edges in order to pass. N squared is way too many. So let's see when an edge will be unnecessary. Okay, so on the right, I drew a diagram. You can look at this diagram in order to get a better understanding. Okay, so in this diagram right here, if AB, which is the length of this red line right here, is bigger than or equal to AC, this red line, and AB is bigger than or equal to BC, yeah, you know what I mean, then edge AB is unnecessary. These three dots represent cows on the coordinate plane, okay? So again, if this edge is bigger than the length of both of these edges, then we will never have to consider this edge. Okay, that's one way we can reduce unnecessary edges. The reason for this is, well, we can use Kruskal's algorithm to prove this, basically. So using Kruskal's algorithm, edges AC and BC will always be picked before AB. That is, if they are picked at all, okay, to be used in the MST, minimum spanning tree. When Kruskal's algorithm encounters edge AB, after encountering these two edges, it will never use the edge AB, right? Because, well, I mean, A and C are already connected, so it's unnecessary to add this. This is not going to be a tree if you add the third edge AB. Okay, so that's one way we can reduce unnecessary edges. Okay, so we can deduce that for any triplets A, B, C, if B dot y equals C dot y, like in here, and C dot x is smaller than or equal to A dot x. So if they're x coordinates, A is on top or on the right of C, then the edge AB will always, and I mean always, be unnecessary. So, okay, that's one observation. The next crucial observation is that the rows, the maximum y coordinate is 10. Smallest is 0, maximum 10. So there are 11 different rows. So then let's view the plane as 11 horizontal rows with rows 0 to 10 with cows plotted on them. Okay, so each cow, can have its y coordinates at the minimum 0 and the maximum 10. So let's plot all 11 horizontal lines. Okay, and plot the cows on them. So let's iterate through the cows in decreasing order with respect to their x coordinates. Okay, so we're going to go through each cow. In this case, will be A, C, B, and D. Okay, on the right, when we're iterating and when we're at cow A, okay, cow A, we will never have an edge A, B. Like what I said here, if B and C are on the same are on the same level and A is on the right side of C or on top of C or below C, then we will never have the edge AB. This applies. Okay, this is okay. So thus, for each row R, we will only have to consider the cow J if it exists, such that first of all, J dot Y equals R. So on each row, when we consider the cow that is on the row, and J dot X is maximal. So on this row, it will be this cow, and cows J and A. Oh, and J dot X is smaller than or equal to A dot X. By the way, the dot X and dot Y here means their coordinates, the cow's X and Y coordinates respectively. We want to make sure that J dot X is smaller than or equal to A dot X. Okay, so the point, for example, if this is J, we want to make sure that it is on the left side or on the same or it has the same x coordinate as A, and cows J and A are different. Okay, so we only have to consider the cows that satisfy these 4 conditions, and we will have to construct edges between A and all of the cows on each row that satisfies these 4 conditions. Okay, so why would that be? Well, because like I said here, if we have B and C on the same row, or if they have the same y coordinate, and A is on the right or on top or on the same if A has the same x coordinate as C, then edge AB will never have to be considered. So here we only have to consider the rightmost cow not past A for each row, and we construct an edge for each one of them. Okay, so for example, on row 8, we will have to construct an edge AC. On row 5, we have to construct an edge AD. Even if there are cows on the left D, we will never have to consider those cows. For example, if there's a cow E on here, we will never have to construct an edge AE, obviously. So yeah, that's the basic solution, and it's pretty understandable too. So let's move straight to the code. I'm going to be using minimum spanning tree algorithms. The algorithm that I will use is called Kruskals algorithm. Pretty sure many of you are familiar with that. And let's see the problem. Let's see the code. I'm going to paste it into the chat so that you guys can see it. So first of all, I have these 3 lines. It's in C++. You should know what these do. Here's n, the maximum value of n. Here's n, the n given an input. LK and SZ denote length and size in the disjoint set union for Kruskals algorithm, because and we have a structure PT which stands for point. We have X, Y, and ID of the point of the cow. Actually, it's basically the same thing, a cow and a point. And then we have a few operators because we want to sort them later on. And we create n of them because we have n cows. And here, remember when we plotted the cows on each row, right? We will keep a vector for each of the rows. We will keep a vector of cows for each of the rows in sorted order. And that's what B does. So B0 is the cows in order on row 0. B1 is the cows on row 1 in order, and so on. Here is the function root. It's part of the string site union. Now I'm going to explain that because I'm going to assume that you understand it. Here is the function square, SQ squared returns a squared. LLDIS, distance between point P and Q. And yeah, here's the make function. We take an n, and for each of the cows, we take in the x and y coordinates of the cow. We set the ID of the cow to be I. It's going to be important later on for the string set union. And we're going to push point AI into row AI.y, its y coordinate. And then we're going to initialize LK, link, and SZ, size, to be I and 1. Those are part of the string set union, right? And then we want to store, of course, all of the vectors, all of the rows of counts, just to make sure that they are in increasing order. Okay, and also it's convenient that they're in increasing order because we're iterating counts in decreasing order, and also vector.pop back in C++ is it's constant. The function runs in constant time, so that's very convenient. And then we have a vector of pairs of points, edges, okay, for the Kruskal function. And then we're going to sort our cows in increasing order, and then we're going to iterate through them in decreasing order, like I said in my slide here. Okay, so first of all, we don't want to have an edge between cow I with itself, right? So we want to remove cow AI.y from the from its vector, from the vector. And then now notice that all the cows are either on the left or at the same x coordinate with cow AI. Okay, because we've already iterated through every cow on the right of AI, and we popped off all of the cows on the right of AI. Okay, so then for each row, we will construct an edge with only the rightmost cow. So for each row or each y coordinate, if there are cows, or if there are any cows in this row, we want to in place back, which is basically push back and then push back a pair. In this case, in edges, we want to push back the cows by.back, the rightmost cow, the last cow in by, and cow AI. Afterwards, we will have about O of 11n cows, which is definitely enough to run Kruskal's algorithm on. We sort the edges in increasing order of their distance, part of Kruskal's function algorithm. And yeah, and here we just go through every edge, see if the two cows that connects are in different sets or disjoint sets. If so, we connect it, and then we add distance PQ to the answer, and then we connect them in our disjoint set, and then we just put the answer in the end, and that's it. So this problem is simple enough. If you guys have any questions, you can ask me. Otherwise, we will be done for the day.
Okay, and that's the end of the workshop. Thank you to everyone who came, and also thank you to Evan and Yizhong for your guys' awesome presentations.